Okay, so now we've talked about the E2 reaction. We're going to move on to talk about the E1 reaction, which is going to be a little bit different. So I'll draw up a general E1 reaction, and then we can talk about what exactly is going on here. So most of the time, we're starting with a tertiary alcohol, and this will be in equilibrium. The thing about E1 reactions is that they're always going to be equilibrium processes, and that's going to lead us to our alkene product. And our byproduct here is going to be water. Okay? So our E1 reaction, what makes it different than the E2 reaction is that it's a stepwise reaction. We're going to have multiple intermediates going from our starting material to our product. Again, just like E2 reactions, E1 reactions favor tertiary substrates. So tertiary substrates are going to be the fastest, then secondary, and then primary. Right? Another unique thing about E1 mechanisms is that you're always going to favor forming the most stable product. So you're always going to obtain the thermodynamic low energy product. Okay, so let's talk about the mechanism. So we're starting with a tertiary alcohol. We don't really have a good leaving group here. So we need to convert the alcohol into a good leaving group in order for this reaction to go. So in this case, we're going to use a very specific reagent the vast majority of the time. And we're going to use concentrated sulfuric acid, H2SO4. Right? So this is going to be a source of H+, so that we can protonate our alcohol in order to turn it into a good leaving group. So we'll go ahead and draw in our H+. So in the first step of the mechanism, we're going to take a lone pair on oxygen and protonate it. And you notice all these steps are going to be equilibrium steps. We'll form the protonated tertiary alcohol, so it looks like we have water attached to our molecule. We know that H2O plus is a good leaving group. So in the second step of our mechanism, we are going to have loss of a leaving group, where we break the carbon-oxygen bond and water leaves. Right? And so when we do this, we're going to form a carbocation. And in this case, we're going to form a tertiary carbocation, so that's going to be a very stable structure. Okay? Now, in the last step, we need to convert our carbocation into our alkene. So what we're going to do, draw in one of the hydrogens. We're going to have to remove a hydrogen so that we can push these electrons in towards our carbocation in order to form the pi bond. So again, this is an equilibrium process. So some base, and it's going to be a very weak base when you're in concentrated H2SO4. There's not many good bases around, so we're just going to describe it as a generic base here. This generic base is going to deprotonate our carbocation, and we're going to take the electrons in the CH bond and sort of fold those in towards our carbocation, and this is going to lead us to our alkene product here. So again, this mechanism has 3 steps going from our alcohol to our alkene. The first step, we are doing a proton transfer. Right? Our second step, we have loss of a leaving group, so we're losing water. And then the last step, we're doing another proton transfer, and we're also forming that pi bond. Okay, so 3 steps: proton transfer, loss of a leaving group, we're doing a last proton transfer, and then forming our pi bond here. Right? So here, the important thing to sort of point out is that our carbocation is the key intermediate here. So the carbocation, all the same rules apply when we talked about carbocations in SN1 reactions. So do watch out for carbocation rearrangements. Right? So if you start with a secondary alcohol, you protonate it, you'd form ultimately a secondary carbocation. If it's possible to do a hydride shift or a methyl shift, you might ultimately form a tertiary carbocation, and you'll obtain a different product. So you do need to watch out for that. Right? The reason we use concentrated H2SO4 is we want to avoid introducing any good nucleophiles here. Right? So this is going to look very similar to what we've already seen with SN1 reactions where we form this carbocation intermediate. So the difference here is that in an E1 reaction, we really don't have any good nucleophiles present. We do generate water, but it's in very small amounts. So it's very unlikely that this is going to act as our nucleophile. So in the presence of concentrated H2SO4, the only thing we really can do is do a deprotonation. If you tried to do this reaction with concentrated HCl, for example, you'd have a lot of chlorine ions around, and those could act as nucleophiles. And instead of getting the E1 elimination product, you'd obtain the tertiary alkyl chloride, which would be the SN1 product. So just to be clear, we really want to use concentrated H2SO4 in order to avoid the SN1 product and go all towards the E1 product.